Welcome back to Very Ordinary Differential Equations. In this lecture, we begin studying higher order linear equations, beginning with constant coefficient homogeneous equations. Let's first discuss some general theory about the behavior of higher order differential equations. An nth order linear differential equation is of the following form. Notice that what we have are a bunch of derivatives of y. That superscript in parentheses refers to the ith derivative of y. Y prime for the first derivative, y double prime for the second derivative are fine, but once you get to about y triple prime, and certainly by the fourth derivative, all those primes are visually unpleasant, so we switch over to this superscript in parenthesis for a higher order derivative. Now our coefficients p0 of x, p1 of x, those are just functions of x, and f of x on the right is still called the forcing function. When that forcing function is constantly zero, as expected, we call the differential equation homogeneous. When the forcing function is not constantly zero, it's called non-homogeneous. This is just as we've done in the past. And a whole lot of the earlier theory like this is going to carry over very directly to the study of higher order equations. We've done first order equations, we've done second order equations, third, fourth, fifth, and so forth. Very much of what we've discussed doesn't have to change very much. So here is our general nth order linear differential equation. This equation is going to be called normal on an interval of x values if the leading coefficient p0 of x has no roots on this interval. So an equation is called normal on an interval of x if the leading coefficient is never zero on that interval. In this scenario, if you pick a point in the interval x0, then the initial value problem has a unique solution provided you have enough information to solve it. And the amount of information we need is, you need to know y at the value, the first derivative at the value, through the n minus first derivative at this x value. Looking up at the differential equation, at a particular value of x0, you need to know y, y prime, all the way through the n minus first derivative. Compare this to what we've done before. For a first order differential equation, you needed to know y at a certain value of x. For a second order differential equation, you needed to know y and y prime at a certain value of x. And all we're saying now is for an nth order differential equation, you need to know y, the first derivative, the second derivative, all the way through the n minus first derivative at a certain value of x. And again, if we replace f of x, the forcing function, with zero, this is called the complementary homogeneous equation to the original differential equation, just as it has been before. And again, here is our linear differential equation. If we have a collection of n different functions, y1 through yn, which solve the complementary equation, which is where the forcing function is set to be equal to zero, and all of those functions are linearly independent, then we call this a fundamental set of solutions. Linear independence is checked through the Wronskian, which is either constantly zero or never zero on some given interval, and this is just how we did it in the past. If y1 through yn is a fundamental set of solutions to the complementary equation, and y sub p is one particular solution to the non-homogeneous equation as written at the top of the page, then we can present all solutions to the non-homogeneous equation through a linear combination of the fundamental set of solutions plus the single particular solution we found. And again, this is exactly how we've done it for second order equations. So we go ahead and begin with the simplest scenario we possibly can, a homogeneous linear equation with constant coefficients. So the forcing function on the right is set equal to zero, and all of the coefficients on the left are just constants. Now for second order equations of this form, specifically a0 y double prime plus a1 y prime plus a2 y equals 0, we know how to find solutions to the differential equation by finding roots of the characteristic polynomial a0 r squared plus a1 r plus a2. So from our second order linear homogeneous constant coefficient differential equation, we make the characteristic polynomial and set it equal to 0. If there were two distinct roots, r1 and r2, then we get two exponential functions as a fundamental set of solutions. If there was one repeated real root, we got e to the rx and x e to the rx as our fundamental set of solutions. And if we found a complex conjugate pair of roots, lambda plus or minus omega I, then e to the lambda x times the cosine or sine of omega x could be taken to be a fundamental set of solutions. So if x minus r is a factor of the characteristic polynomial, however x minus r squared is not, then we add e to the rx to the fundamental set of solutions. So x minus r to the first power is a factor, x minus r squared isn't, we add one function e to the rx. If x minus r squared is a factor of the characteristic polynomial, but notice x minus r cubed certainly can't be because the characteristic polynomial is only of degree 2. So x minus r squared is a factor, x minus r cubed is not. We add two functions, e to the rx, x e to the rx. And when we have an irreducible quadratic, x minus lambda squared plus omega squared, as a factor of the characteristic polynomial, then we add a single pair of functions, e to the lambda x cosine and sine of omega x to the fundamental set of solutions. This is how we're going to generalize to higher order equations. So let's discuss how to generalize those ideas of factors of the characteristic polynomial to higher order equations. So here is our differential equation, homogeneous linear constant coefficients. We form from it the nth degree characteristic polynomial. If x minus r to the k is a factor, but x minus r to the k plus 1 is not. So this exponent k refers to the largest power of x minus r that can be factored out of the characteristic polynomial. Then we add k distinct functions according to this root r. E to the rx, x e to the rx, x squared e to the rx, all the way up to x to the k minus 1 e to the rx. Now notice, with this power being k, we go up to x to the k minus 1. Because we began at a power of x to the 0 times e to the rx, this is a collection of k linearly independent functions that we're adding to the fundamental set of solutions, corresponding to x minus r to the k being a factor, but x minus r to the k plus 1 not being a factor of the characteristic polynomial. Similarly, if you have an irreducible quadratic to the k, which is a factor of the characteristic polynomial, but the next power is not, then we add k distinct pairs of functions, beginning with e to the lambda x cosine and sine of omega x, but then we multiply both of those by x, and so forth, all the way up to multiplying by x to the k minus 1. So here we have x linearly independent pairs of functions corresponding to this irreducible quadratic to the kth power, being the largest power that could be factored out of the characteristic polynomial. Now, creating a set of functions according to that technique will create linearly independent functions, and they will solve the differential equation, assuming that you factored the characteristic polynomial correctly. Therefore, solving homogeneous linear differential equations with constant coefficients of order n is only a problem of factoring polynomials of degree n. So remember all of the old techniques you've learned before for factoring polynomials, like long division, synthetic division, and the rational roots theorem, among others. As a first example, let's find a fundamental set of solutions to the given differential equation. Well, we start by making the characteristic equation, the characteristic polynomial, set equal to 0. However many derivatives of y we've taken, that's the power of r, including y itself being r to the 0, or just the constant. So we have r to the 4th plus 5r cubed plus 5r squared minus 25r minus 26 equals 0, and we need to now factor this polynomial. Now, according to the rational roots theorem, since all the coefficients are integers, any rational root must be of the form m over n, where the numerator is a factor of the constant term, which is 26, and the denominator must be a factor of the leading coefficient, which is 1. Now, factors of 26 are 1, 2, 13, and 26. Factors of 1, just 1. So here is a list of all possible ratios, plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 13 over 1, plus or minus 26 over 1. Now this is 8 different numbers. They can't all be roots, but we can just test all of them. And if we simply test them all by hand, we'll find that r equals minus 1 and r equals 2 are roots, but none of the others are. So the only possible rational roots are r equals minus 1 and r equals 2. This doesn't mean it's the only roots. However, they are the only rational roots. With those known roots, we can therefore factor an r plus 1 and an r minus 2 out of the characteristic polynomial, possibly more than once. So we're going to factor them out as many times as we can. So here is our characteristic polynomial set equal to 0. We factor r plus 1 through long division. We're only going to go through the long division once. So here it is. With our characteristic polynomial and our known factor, how many r's would I need to multiply by to get r to the fourth? I would multiply by r cubed. Multiplying r cubed here gives me r to the fourth and r cubed. I subtract this down. R to the fourth minus r to the fourth is 0. Great, that was the point. 5r cubed minus r cubed is 4r cubed. What do I need to multiply this by to cancel out 4r cubed? Well, I need to multiply by 4r squared. When I do, I get 4r cubed plus 4r squared. I subtract that. This cancels here. 4r cubed minus 4r cubed. That was the point of multiplying by 4r squared. 5r squared minus 4r squared gives me r squared. What do I need to multiply r plus 1 by to cancel out this r squared? I need to multiply it by r. When I do, the product here becomes r squared plus r. The difference, r squared minus r, is 0. Good, that was the point. Minus 25r minus r gives me minus 26r. What do I need to multiply this factor by to cancel out minus 26r? I need to multiply it by minus 26. And when I do, I get minus 26r minus 26. Everything cancels out, meaning I have no remainder, so everything went just as it was supposed to. This is the only time we're going to go through the long division in these videos. This should be review. This should be something you can do on your own. So having done that long division, our characteristic polynomial has now been factored as r plus 1 times a cubic, r cubed plus 4r squared plus r minus 26. That cubic term, however, if you try plugging minus 1 into it, does not give us a 0. So the cubic term does not have negative 1 as a root, meaning r plus 1 cannot be factored out of it. But we already knew that r equals 2 is a root of the original characteristic polynomial. So r equals 2 is a root of this, and it's certainly not a root of r plus 1. So r equals 2 must be a root of this cubic term, and indeed you can go ahead and verify that it is. Now this means that r minus 2 can be factored out of that cubic, and we're not going to show the details. Once you factor r minus 2 out of the cubic, what's left behind is r squared plus 6r plus 13. Now that's a quadratic which is irreducible. How do we know it's irreducible? The long answer is the only possible rational roots of our original characteristic polynomial was a long list, and we computed all of them, finding negative 1 and 2 were the only possible rational roots. You can verify that negative 1 and 2 are not roots of this, meaning this quadratic does not have any rational roots, but it might have irrational roots. How do I know it doesn't? Well, we can use the quadratic formula. If I apply the quadratic formula to this quadratic polynomial, we'll find out that it has no real roots. Also, you can complete the square on it. R squared plus 6r plus 13 can be represented as r plus 3 squared plus 4, or plus 2 squared. And since this is one square plus another square, it can't be equal to 0, and therefore there are no roots. So we have factored this completely as the linear r plus 1 times a linear r minus 2 times an irreducible quadratic r plus 3 squared plus 2 squared. So r plus 1 is a factor with multiplicity 1. Therefore, e to the minus x goes into our fundamental set of solutions. R minus 2 was a factor with multiplicity 1. E to the 2x goes into our fundamental set of solutions. And the irreducible quadratic r plus 3 squared plus 2 squared has multiplicity 1. So e to the minus 3x times the cosine and sine of 2x go into our fundamental set of solutions. So overall, we have a fundamental set of solutions given by those four functions: e to the minus x, e to the 2x, e to the minus 3x cos 2x, and e to the minus 3x sine of 2x. With our fourth order differential equation, we have a fundamental set of four functions. For a second example, find a fundamental set of solutions to the differential equation given here. Then write a general solution to the differential equation. Well, we set up our characteristic polynomial and set it equal to 0. R to the 7th plus 3r to the 6th plus 5r to the 5th plus 7r to the 4th plus 7r cubed plus 5r squared plus 3r plus 1 equals 0. If there are any rational roots, the numerator must be a factor of the constant term, which is 1, and the denominator must be a factor of the leading coefficient, which is 1. That's a pretty short list of possible rational roots. Plus or minus 1 are the only possible rational roots. By inspection, we will see that negative 1 is a root, which means r plus 1 can be factored out. So let's go ahead and factor r plus 1 out of the characteristic polynomial. If you go ahead and factor that out using long division, you'll get this, okay, leaving behind a 6th degree polynomial. By inspection, you can plug -1 into that 6th degree polynomial and see that it's a root again, meaning r plus 1 can be factored out again. Do the long division, and you'll get this. So now I have 2 factors of r plus 1 and a 5th degree polynomial. It's still a root of that leftover 5th degree polynomial, so factor r plus 1 out again. Now we have r plus 1 cubed times r to the 4th plus 2r squared plus 1. Now this quartic on the right does not have any rational roots. The only rational roots that were possible were plus or minus 1, and neither of them are going to be roots of that. So we factored the characteristic polynomial as r plus 1 cubed times r to the 4th plus 2r squared plus 1. And that quartic has no rational roots. Now, factoring a degree 4 polynomial with no rational roots could, in general, be a rather difficult problem. However, r to the 4th and r squared are never going to be negative, and then we're adding this 1 on. So r to the 4th plus 2r squared plus 1 is always at least as large as 1, meaning it's never 0 at all. This quartic polynomial does not have any real roots, rational or irrational. Therefore, it must be expressible as a product of irreducible quadratics. Now, in general, this is a very difficult problem, figuring which irreducible quadratics go into things. However, by inspection, it's just r squared plus 1 squared. Observe that here I have r squared squared, 2 r squared plus 1. So if t, for example, was r squared, I'd have t squared plus 2t plus 1, or t plus 1 squared. If you're comfortable working with complex numbers, by the way, there are techniques for factoring these quartic polynomials that might be helpful. But very few people know them. I've certainly never worked with them in any great detail. At this point, it's just a matter of getting lucky. And we see that it can be factored as r squared plus 1 squared. So here is our total factoring of the characteristic polynomial, r plus 1 cubed, and then the irreducible quadratic r squared plus 1 squared. So since we've completely factored the characteristic polynomial, we can make a fundamental set of solutions. From r plus 1 cubed, we get e to the minus x, x e to the minus x, x squared e to the minus x. 3 terms corresponding to this linear power with power 3. From r squared plus 1 squared, we end up with cos x and sine x, but then also times x, because this exponent here of 2 tells me this pair of functions has to appear again with a higher power of x out in front. And now we have 7 functions in our fundamental set. We started with an order 7 differential equation, and these 7 functions are all linearly independent. With a fundamental set of solutions given, we can now construct a general solution. The general solution y is simply given as a sum of various constants times elements of our fundamental set of solutions, c1 e to the minus x, c2 x e to the minus x, and so forth. For our third example, let's solve an initial value problem. Y triple prime minus 9y double prime plus 27y prime minus 27y equals 0, with the information that y of 0 is 1, y prime of 0 is 2, y double prime of 0 is 3. Well, we set up our characteristic polynomial and start factoring it. After we do some work, kind of glossing over that point, it factors as r minus 3 cubed. Since we have r minus 3 to the 3rd power as our characteristic polynomial, a fundamental set of solutions is given by e to the 3x, x e to the 3x, x squared e to the 3x. Now that we know our fundamental set of solutions, we can set up a general solution. A general solution is given by a constant times e to the 3x, another constant times x e to the 3x, and a third constant times x squared e to the 3x. So we've determined that a general solution is given by the following expression, but there are 3 constants whose values we don't know. It's time to start using the initial values. So we compute y prime. All right, this is a constant times e to the 3x, so its derivative is 3, constant e to the 3x. Here we have an x e to the 3x. Okay, so up to factoring out this constant c2, the derivative of x e to the 3x is going to be 1 plus 3x e to the 3x, and the derivative of x squared e to the 3x is going to be 2x plus 3x squared e to the 3x. Similarly, we compute y double prime. After some simplification, it can be expressed as follows. And now we can start using those initial values. Let's take a look at the first line. So here is our expression for y, but y of 0 is 1. So if I plug in x equals 0, this term will vanish, this term will vanish, e to the 0 is 1. So we simply get y of 0, which is 1, but over here we just get c1. So very quickly we determine that c1 must equal 1. Next, let's use the fact that y prime of 0 is 2. So we're going to go ahead and substitute x equals 0 into this line right here. E to the 0 is 1. This x being 0 will kill this term, but we will get a c2 times e to the 0. Here we'll get 2c3 times 0, 3c3 times 0 squared. Everything here will vanish, giving us just 2 is equal to 3c1 plus c2. But we've already determined that c1 is equal to 1. So with c1 equals to 1, we can solve for c2 is equal to minus 1. And then let's go ahead and use y double prime of 0 is 3 by taking this expression for y double prime and setting x equal to 0. 3 is equal to 9c1 times 1 plus 6c2 plus 0 times e to the 0 plus 2c3 plus 0 e to the 0. Altogether, 3 is equal to 9c1 plus 6c2 plus 2c3. Since we already know the values of c1 and c2, we can go ahead and solve, and we find that c3 is actually 0. So we determined that c1 is 1, c2 is minus 1, and c3 is 0. Therefore, our solution can now be written quite explicitly. E to the 3x times 1, x e to the 3x times minus 1, and x squared e to the 3x times 0, or just y is equal to e to the 3x minus x e to the 3x. So let's discuss what we covered. In general, when you are given higher order differential equations, ideologically, things proceed very much as they did for second order differential equations. For example, it's still of great interest to solve the complementary homogeneous equation because the space of all solutions to the complementary homogeneous equation is still spanned by a fundamental set of solutions, a sufficiently large collection of linearly independent solutions. In the situation of a homogeneous linear equation with constant coefficients, finding a fundamental set of solutions totally reduces to can you factor the characteristic polynomial. And factoring the characteristic polynomial will give you roots of certain orders, and then you will also have irreducible quadratics to certain powers. Those higher powers simply relate to multiplying elements of our fundamental set of solutions by an increasing sequence of powers of x, which is a very natural generalization to all the techniques we learned for second order differential equations with constant coefficients.